everyone. In the previous class, we had seen the synthesis of amines and various methods through retrosynthetic analysis how we can synthesize amines. In this discussion, we will be looking for alkene synthesis. How are these alkenes generally synthesized? They can be synthesized by the elimination from alcohol and their derivatives. Basically, the reaction that will be going on would be a system like dehydration. Then when I say it's a dehydration, it should happen under acidic condition, because if there is a presence of OH, then I need to protonate that OH and I can remove a molecule of water. Now this would mean that the alcohol has to be assembled by usual methods. This method is particularly good for cyclic or branched olefins. When I say olefins, that means it is alkene systems that I am going to look. Now for example, if there is a presence of a cyclohexanone system, when it reacts with a Grignard reagent like RMgBr, it is going to give me a cyclohexanol system, that is compound number 1. Under protonation, that is when the compound undergoes a protonation reaction, this proton is going to be attacking on the OH system, so that the elimination takes place by the removal of this OH system and we get an alkene system. For this job to happen, that means for the synthesis to be an alkene system, the acids must be fairly strong and they must have a non-nucleophilic counter ion or substitution may occur. Now if there is a nucleophile along with an acid system, now for example, if I say H plus and Cl minus, that is an HCl as an acid, Cl minus can act as a nucleophile and further substitution may take place. So that should not happen. So substitution must be avoided and there should not be any nucleophile in the system. Hence, it should be non-nucleophilic counter ion should be present, so that alkenes could be synthesized easily. Example for such an acid where alkenes can be synthesized easily can be KHSO4, phosphoric acid, POCl3 in pyridine. Generally, when I try to synthesize an alkene system, double bond in the 6-membered ring, that is when I observe this compound number 2, double bond inside the 6-membered ring is greatly preferred to one outside and only cis is possible. Now when I say that 6-membered ring, the bond which is endo in the 6-membered ring system is more stable than that of an exo bond system. If I want to do the retrosynthetic analysis of this cyclohexene system, now this is the cyclohexene system. Under functional group interconversion, I can convert it into its respective alcohol. 1,1-CIX if I do, I will be getting my starting material or synthon as cyclohexanone and RMgBr as the Grignard reagent, which can be my synthetic equivalent. When we go for the synthesis of this, cyclohexanone reacts with the Grignard reagent to give me my alcohol under protonatic condition. So what happens in the protonating condition is, when the H plus is going to attack an OH, I will be getting an OH2. That means I can now remove a molecule of water under dehydration to get me my target molecule, that is my cyclohexanone system. Under similar grounds, we can synthesize n number of alkenes. Now for example, if I have got an alkene like this, which is a highly hindered alkene because of the presence of these two phenyl system. Under functional group interconversion, now this double bond can be synthesized under functional group interconversion by just converting it into an OH, that is an tertiary alcohol. Upon 1,1-DIX, that means 1,1 group disconnection, I can easily remove these two phenyl system and I can convert them into the respective Grignard reagent, that is 2PHMgBr. Upon whatever is remaining, now I can just convert it into its respective ester system. So under the retrosynthetic analysis, I can end up with an ester synthesis, ester system as a synthetic equivalent and a Grignard reagent. Under the synthesis of this particular target molecule, ester reacts with two molecules of Grignard reagent, that is 2PH MgBr. It is going to give me an tertiary alcohol. This tertiary alcohol, when it reacts with a non-nucleophilic acid like POCl3, it is going to give me my target molecule. Now, elimination on alkyl halides follows essentially the same strategy as the halide is usually made from alcohol. When I say the halide is usually made from alcohol, that means the X in the halide system can easily be replaced. That means once the elimination takes place, easily we can observe that I can synthesize an alkene system, and hence elimination with alkyl halides is nothing but elimination of an halide system so that an alkene is being synthesized. Now for example, if this is my target molecule which is having my alkene system, under functional group interconversion I can convert this into an halide system. Under functional group interconversion, this Br can undergo a substitution reaction and Br can be converted to an OH system. Now OH is not a very good leaving group. Rather than that, what we would convert this OH into an epoxide system. We have already seen an epoxide system as a good Ampoulang reagent. In turn, when a Ampoulang reagent like epoxide is present, I can easily open this three-membered ring by attacking with a Grignard reagent so that I get a long chain system. How we can do this under the synthesis of the system? Grignard reagent like RMgBr would attack the epoxide system to give me this long chain alcohol. This long chain alcohol, under the influence of phosphorus tribromide, it is going to give me an alkyl halide. Alkyl halide in the presence of a stronger base like tertiary butoxide system undergoes an elimination reaction to get me my target molecule, that is an alkene. So this is another way of the synthesis of alkenes, making use of an halide system. In the previous system what we made use by a dehydrating system, whereas in this particular system I am making use of an alkyl halide system. A very common example of the synthesis of an halide system, of an alkene system, of an alkene system. A very common example for the synthesis of an alkene system would be a system called as Wittig reaction. Now this particular named reaction is a very known reaction for the synthesis of alkenes. When I say this is a very known reaction, that means it's a very famous named reaction under which an alkene system could be synthesized. For this particular synthesis of an alkene system through a Wittig reaction, George Wittig in the year 1979, he got a Nobel Prize for this particular system. That means he tried to synthesize an alkene system, and hence in the due course he got a Nobel Prize. Now what does this Wittig reaction generally have? You have already seen this Wittig reaction under phosphonium ylide systems of your named reactions, in which it is nothing but conversion of a carbonyl compounds like ketones or aldehydes to alkene system. What is the intermediate that will be making use of? Phosphonium ylide system. Now ylides are nothing but positive and negative charges are present over there only. When we say this pH, it means we have a phenyl system. Now this phosphonium ylide system easily can attack onto the carbonyl carbon. Further, they can give me an alkene system. Now for example, if I am observing a carbonyl system, if there is a presence of a carbonyl carbon, ylide can attack, that is negative charge on the ylide can attack onto the carbonyl carbon. In turn, it is going to give me an alkene system, and the byproduct that I am going to get is triphenyl phosphine oxide system. So this is the way through a retro-Wittig reaction. The meaning of retro-Wittig reaction is I will be trying to go backward in the reaction. That itself is called as a retrosynthetic analysis. Wittig reaction is nothing but a forward reaction. Retro-Wittig meaning we will be coming backward so that we can get the synthetic equivalents. Now when I come to a more deeper discussion of a Wittig reaction, now I can observe that if there is a presence of a cyclohexenone system, it can be attacked by a phosphonium ylide system. Negative charge on the ylide system attacks onto the carbonyl carbon. This gives me a structure called as betaine structure. Betaine structure is nothing but oxygen carries a negative charge, phosphorus will be carrying a positive charge. Negative charge on the oxygen can now be passed on to phosphorus. How this happens? Because phosphorus can hold the extra electrons in its empty d orbital system. This is going to turn in such a way that it is going to give me this 4-membered ring. Now this 4-membered ring is definitely not stable because of the spherical hindrance. We can observe that because of the lot of ring strain and spherical hindrance system, the 4-membered ring is not stable. Now what exactly has happened over here is, it is a cycloaddition product formed by 2+2 system between carbonyl carbon and ylide. What is happening in this step number 1 is nothing but the reaction, that is cycloaddition, which is 2+2 system, attack onto the negative charge onto the carbonyl carbon takes place, so that I get a betaine structure. It is going to lead to me a 4-membered structure. If I do a reverse 2+2 cycloaddition to this particular system, that means if I try to do a reverse 2+2 on this 4-membered ring, I will be able to get an alkene system and I will be able to get a triphenyl phosphine oxide as my byproduct. The byproduct that I am going to get is triphenyl phosphine oxide. So in this way, reverse 2+2 cycloaddition takes place and the 4-membered ring breaks down, so that one of the product will be an alkene system, the other product is called as triphenyl phosphine oxide. So this is what is called as a Wittig reaction. The intermediate involved in the Wittig reaction is called as betaine system. Now if I consider this alkene system as my target molecule, now I can observe that there is a more substituted system and there is a lead substituted system across the double bond. How I can do a disconnection approach? Obviously, I will be cutting down at the double bond system, so that I get a cationic system which is 2+ and 2- anionic system. I can easily generate this cationic system by making use of a cyclohexenone as my synthetic equivalent. The other system can be easily a phosphorus ylide system. How this phosphorus is useful is, phosphorus can use its empty d orbitals to accommodate the extra electrons. This is useful when in the next step of making of the betaine system. Now if we have observed here, we have done a betaine system here. Further, when this oxygen transfers its extra electrons onto phosphorus, we can observe a 4-membered ring. This happens because phosphorus has got a d orbital system which can hold the extra electrons, and in turn it can give me a 4-membered ring. Now exactly when I look at various example making use of this Wittig type of reaction and undergoing a retro-Wittig reaction, I can observe that there is a phosphonium ylide which is substituted phosphonium ylide and there is a carbonyl carbon. Now this is an aldehydic system. This is orthohydroxybenzaldehyde reacts with this phosphonium ylide. In turn, there is a betaine structure which gets formed. This betaine structure, upon the movement of the electrons from oxygen to phosphorus, will lead to this 4-membered ring. Further, upon the cleavage, that means doing a reverse 2+2 cycloaddition reaction, I will be getting a triphenyl phosphine oxide and a Wittig reaction which is going to give me my alkene system. This alkene system, further, if I can utilize this alkene system, I can easily cyclize the system. There is a presence of an OH over here. Definitely in the presence of a base, the proton can be abstracted. This proton now will be cleaved away, so that a negative charge is generated on oxygen. Oxygen can now attack the carbon, so that bromine acts as a leaving group. In turn, the cyclization takes place to give a chromine structure. So this is one of the classical examples for the synthesis of chromine structure, which looks like a coumarine structure. What we have done here is, orthohydroxybenzaldehyde reacts with the phosphorus ylides to give me a butane structure. This in turn is going to give me a 4-membered ring. There is a reverse 2+2 cycloaddition reaction, so that I will be getting triphenyl phosphonium oxide system, and a Wittig reaction which is going to give me an alkene system. Further, because there is a presence of an OH group, what happens is, in the presence of a base, this proton is abstracted. Negative charge is generated on oxygen, which attacks onto the carbon, and bromine acts as a leaving group, cyclizing the system to give me a chromine structure. How can we do this target molecule, that is chromine structure, and its retrosynthetic analysis? Now there can be two choices. One choice is to cleave between benzene and oxygen, the other choice is cleaving here, that means C single bond O. The choice attached to benzene is not a very good choice. This is because what happens is, the aromaticity of the benzene gets disturbed over there. Instead of that, we will be doing a retrosynthetic analysis and we will be cleaving a C single bond O, generating a negative charge on oxygen and a positive charge on carbon. How it can be further done to through a synthetic equivalent is, oxygen can be turned into OH and positive charge on carbon can be turned by substituting it by Br or a halide system. CX atom bond should be disconnected in preference. This is because we do not want to touch the aromaticity of benzene. In turn, I want to cleave it safely. Making use of an Ampulam concept, plus minus plus I can make use, and further again I can cleave at the C double bond C. This is going to give me C single bond C cleavage, C double bond C cleavage, which is going to end up in an aldehydic system, and it is going to give me an ylide system. So these two becomes my synthetic equivalents. One is orthohydroxybenzaldehyde, the other one is phosphonium ylide, so that I will be able to achieve my target molecule. How we can achieve this target molecule we have already seen. Making use of the synthetic equivalents, that is substituted aldehyde reacts with phosphonium ylide further to give me my chromine structure. In this way, we can utilize alkene system in the retrosynthetic analysis through various systems. One can be making use of a dehydration system. Second can be making use of an halide system. Third can be making use of a retro-Wittig reaction. Alkenes can be synthesized through a retrosynthetic analysis. This concept now further leads to use of acetylenes. When I can look for a double bond system, definitely I need to look for a triple bond system, that is C triple bond C. That means we have to look for acetylene system. Now when I say acetylene system, we have to look how the acetylenes can be used. Now commonly these acetylene system under the reaction like sodamide, NaNH2 in the presence of liquid ammonia, an anion is synthesized and a cation is synthesized. That means this proton can be kicked out and then I can get a positive charge. If this alkene system reacts with a Grignard reagent like ETMgBr, that means ethyl magnesium bromide, it is going to give me an acetylene Grignard reagent. So why this is very important is because acetylene itself is readily available and its first important property is its ability to form an anion. This is because anion can be easily formed, usually with sodamide in liquid ammonia but also with Grignard exchange. We have easily observed that if I make use of soda amide or if I make use of a Grignard reagent, I can easily generate an anionic system. This is one of the few carbanions available as a genuine intermediate. That means this intermediate can be easily synthesized and it will react with n number of systems like alkyl halide system, carbonyl carbine system, epoxide system to get me various intermediate system. Now for example, once an acetylenic anion is generated, how this gets generated? Either the acetylene can react with sodamide system or in the presence of Grignard reagent. This anion can react with alkyl halide to give me substituted acetylene system. Secondly, This anionic system can easily attack onto the carbonyl carbon. We can observe that negative charge can attack onto the carbonyl carbon, so that I can easily get a tertiary alcohol. The anionic system can easily attack onto the epoxide system, so that a ring opening reaction takes place and I get an alcoholic system. These products still have an acetylenic proton, so they can react again with the base and an electrophile. Now when I observe the products, there is an acetylenic proton. This proton also can be replaced easily, and further they can react to give me other substituted acetylenic compounds. Now for example, if I make use of this substituted acetylenic system, this reacts in the presence of sodamide, it is going to generate me an anionic system. This anionic system attacks onto the carbonyl carbon to give me a tertiary alcohol, which is substituted acetylenic alcohol, which is substituted system. In this way, acetylenic systems are very important in terms of getting a dianionic system by replacing one proton at a time. An example under the synthesis of this type of acetylenic system is called as an oblivion system. Now this is my target molecule. This is called as oblivion system. It consists of an OH and an acetylenic system. I can easily cleave it as an acetylenic system, so that I will have a carbonyl carbon and an acetylenic system. Why easily we can cleave it? Because OH can be converted into a carbonyl carbon through 1,1,CC disconnection, and acetylenic system can be easily substituted in such a way that because an anion can be generated on to the acetylenic system. Now for example, this oblivion system, I can cleave at a C triple bond C, converting this OH into its respective functional group interconversion through a carbonyl carbon. The other synthetic equivalent can be an acetylenic system. How to do its synthesis is, acetylene reacts with sodamide in the presence of liquid ammonia. It reacts with an ketonic system, that is ethyl methyl ketone. It is going to give me my target molecule, because once this anion is generated, it can easily react onto the carbonyl carbon to get me my target molecule. This is how the target molecule oblivion can be synthesized. The other example is called as sulfinol. Now this sulfinol system is nothing but it's a long chain tertiary alcoholic system. Now this tertiary alcoholic system can be observed that there is a presence of a C triple bond C, there is a presence of a ditertiary alcoholic system. Its retrosynthetic analysis is very easy. It has to be cleaved between C single bond C and a C triple bond C system. This cleavage at a point where this acetylenic system is being attached, this turns this OH into a carbonyl carbon, and other synthetic equivalent is the acetylenic system. How do we synthesize this sulfinol system is, acetylene in the presence of base, it is going to generate an anionic system. This anionic system attacks onto the carbonyl carbon, so that one of the tertiary alcohol can be synthesized. In this intermediate, obviously there is the presence of another proton. This acidic proton can be easily abstracted by the base. This base will abstract this proton. It is going to generate an anionic system. The anion now easily attacks onto the carbonyl carbon to get me this diol system or my target molecule. In this way, sulfinol system can be synthesized by making use of 2 moles of the carbonyl carbon and 2 moles of a base in the system, and an acetylenic system, which is very important by losing its acidic proton. Now once again, if I want to observe this sulfinol analysis, I will be cleaving at C single bond C, ending up with a carbonyl carbon and an acetylenic system. One time the anion is synthesized because there is an abstraction of a acidic proton attack onto the carbonyl carbon. A monoalcohol is synthesized. There is a presence of another acidic proton which is again abstracted by the base, so that this anion gets generated and gets attacked onto the carbonyl carbon to give me a diol system, which is my sulfinol or my target molecule. Now in the same way, disubstituted alkenes can also be synthesized. Now if I say disubstituted alkenes, definitely there will be two choices. Through an alkyne system, I am trying to synthesize a disubstituted alkene systems now. Either it can be a cis-alkene system or a trans-alkene system at will, because monosubstituted acetylenes can be hydrated to methyl ketones. Now we can observe this, that acetylenic system can be converted into C double bond C, that is C triple bond C. Upon reduction, I can observe that I can easily convert it into its respective C double bond C system. Now for example, if there is an acetylenic system which is an substituted acetylenic system under Lindlar's catalyst, that is hydrogen, palladium and barium sulfate, in the presence of quinoline as a poison, I will be able to get a cis alkene system. The same alkene system in the presence of sodium and ammonia is able to give me a trans alkene system. If there is a substituted alkene system in the presence of a substituted alkyne system in the presence of a protonic environment and mercury, in the presence of hydrating system like water, alkene system can be converted to its respective carbonyl carbon. So the alkyne system can easily give me a cis system, that is cis alkene system, and a trans alkene system. Also the alkyne system is easily able to give me a carbonyl carbon upon hydrolytic condition. Now if I want to look at an example, for example, if there is a cis butene diol, this can be made by the hydrogenation of the corresponding acetylenic system. The butyne diol is made commercially by a catalytic process. Now when I say I want to synthesize this target molecule, now I want to do a cis butene diol, how will I do a retrosynthetic analysis? The target molecule under functional group interconversion, this double bond system can be converted to a triple bond system, that is C triple bond C system. That is my alkyne system. Further, upon a C single bond C cleavage, it is going to give me one synthetic equivalent as an acetylene system. The other synthetic equivalent is formaldehyde system. When I cleave these two systems, one of the synthetic equivalent is the formaldehyde system, the other synthetic equivalent is the acetylenic system. So the target molecule under functional group interconversion, it gets converted to an acetylene system. Further, the synthetic equivalents would be acetylene and formaldehyde system. So how can I synthesize this cis butene diol? Acetylene reacts to a formaldehyde system in the presence of a metal catalyst. This is going to give me my acetylene diol system. In the presence of Lindlar's catalyst, that is hydrogen, palladium and barium sulfate with quinoline as a poison, it is going to give me cis butene diol system. Now we can observe that this is going to give me a cis butene diol system because I am making use of a Lindlar's reagent. Definitely, utilization of a Lindlar's reagent, it is easily going to give me my cis diol system. Now, the same system, if there is a presence of a bromide system, under functional group interconversion, what is going to happen is this bromide can be converted to an OH system. Further, there can be two choices. Now, when I have got the substituted bromide, I can have A or B. Easily, I can cleave out this B system or I can make use of A system so that I can get an acetylenic and ETBR system. So this way the synthesis can require the alkylation of dianion on carbon. Now how can I synthesize this particular system is, it is going to require the alkylation of dianion on carbon. This is where the alkylation does occur as a carbanion. Why this will happen is because pKa of acetylenic system is approximately 25. That is much more reactive than the oxyanion system, because oxyanion has got a pKa of almost just 16. This means the acidity of acetylenic system is more than that of that oxyanionic system. and the protection of alcohol becomes unnecessary here. So let us see how I can synthesize this type of substituted alkyl system. This acetylenic system reacts with butyl lithium. What happens is there is a presence of a proton. Now this proton system, I can observe that the alcohol as my starting material. What I have been picking up is, I will be picking up the OH. Now substituted acetylenic alcohol I will be picking up in the presence of butyl lithium. OH is present. Obviously what is going to happen is, it is going to give me, this OH is present, it is going to give me a proton system in the presence of base. Abstraction of a proton takes place and O minus is generated now. This reacts with ethyl iodide in the presence of hydrating conditions. Oxygen can easily attack onto the ethyl system, so that iodine acts as a leaving group. In turn, I will be able to get an acetylenic system. In turn, if I can get an acetylenic system in the presence of PbR3, I can easily synthesize my target molecule. So this is how substituted acetylenic bromide systems can be easily synthesized, and just making use of a suitable basis and making use of the pKa of acetylene, which is more acidic than that of an oxyanion system, I can easily be able to synthesize the acetylenic system. So in this particular discussion, we have seen how the synthesis of alkene system can be done, and how the use of acetylenic system is going to give me various intermediates, and how this acetylenic system is going to react with various intermediates so that I get a useful final products. And finally, how a particular target molecules like sulfonol system can be synthesized. So through this, we come to the conclusion of my part of the retrosynthetic analysis. Thank you.